Okay, we're going to continue on here. Chapter 12, we got into last time. Chapter 12 was about bonding. And we talked about really the two types of bonding that we come across, which is ionic bonding. And with ionic bonding, as we talked about, really the way you could always know that it's going to be ionic bond is basically if you have this combination here. So if you got a metal and a non-metal together, that's pretty much all the information you need to know that it's going to be ionic. And remember, with ionic bonding, what we get, because of the difference in those kind of periodic trends, we will always get, again, a transfer of electrons from the metal to the nonmetal. The result of that, again, is going to create a cation, which is positively charged, and an anion, which is negatively charged. And that is, again, what's going to hold that ionic compound together, the opposite in attraction there between the two charges. Again, sometimes referred to as electrostatic attraction. And again, the main thing is there is no sharing of electrons here. So again, in an ionic bond, we have no sharing of electrons. We have a complete transfer of electrons, always from the metal to the non-metal, maybe one electron, two electrons, however many electrons. But it is that transfer of electrons which then creates the ions, which is what holds that sort of bond together. And that's different than the other type of bond we talked about, which is really a covalent bond. And the covalent bond is really between two nonmetals. And if you kind of look on the periodic table, all the nonmetals are sort of in the same location up there in the upper right of the periodic tables, which means, again, they do share pretty similar periodic trends in terms of what they want to do with their electrons and what they want to do with gaining electrons. And because they both basically would have the same or similar trends, which means that they both really want to hang on to their electrons and they want to gain electrons, we do get here sharing of electrons. So that's the major difference between the two types of bonding. When two nonmetals are together, we get sharing of electrons rather than transfer of electrons. And as we talked about last time, that sharing of electrons may be equal. And when we have equal sharing of electrons, uh, that is what is known as a nonpolar covalent bond. So a nonpolar covalent bond, or just a nonpolar bond, is where you have sharing of electrons between two atoms, and they're basically shared equally. So sort of the consequence of a nonpolar bond is kind of like a neutral bond. There's not like a negative side or a positive side. Everybody's kind of sharing everything equally, and we have really equal distribution of those negatively charged electrons. That's different than when they can also be shared. Unequal sharing can also occur. And when we have unequal sharing occurring, that is what is known as a polar covalent bond, or just a polar bond. And in a polar bond, what that means is we are not going to get basically equal sharing of electrons. So the electrons are going to be closer to one atom in that bond than the other. And that is going to be based on electronegativity. And remember that electronegativity is the ability of an atom basically to bring electrons towards itself. It increases as you go this way, and it decreases as you go this way on the periodic table, with fluorine being the most electronegative. The result of this sort of unequal sharing of electrons or polar bond is in a polar bond, we will get really that separation of charge. So we talked about like HF, for example, fluorine being the more electronegative, will create a more partially negative charge on the fluorine and then more partially positive charge, let's put that out, on the hydrogen there. And that again is based on the unequal sharing of electrons that are occurring. So we could also represent this with an arrow, and this is sometimes referred to as a dipole arrow, where it points to the more negative side of the bond. And again, the back part of this arrow that makes kind of a positive sign to the more positive side of that bond. Now, we could actually use electronegativity values to calculate what type of bond that we would expect. Thank you. And for example, we could calculate the difference in electronegativity values. Electronegativity values run from 0 to 4. 4 is the most electronegative, and 0 is not so much. And if you got a difference of 0 to like 0.4, that's going to be considered a nonpolar bond. And it's going to be equal sharing of electrons basically happening here. If you're above 0.4, like 0.5 to less than 2, that is some type of polar bond, which means you're not going to have equal sharing of electrons. You're going to have unequal sharing of electrons, which means that you again are going to get this charge separation. And the last thing that we talked about here was, you could have above 2, which, as we also talked about, is not a perfect sort of cutoff. But typically, if you're above 2, that's going to be an ionic bond, and you're going to have this transfer of electrons. Remember, you don't really need this because if it is a metal and a non-metal, it's going to be ionic, and that's really all you need to sort of know there's going to be an ionic bond. You also remember that when you're looking at electronegativity, you don't necessarily have to always have the numbers to make an educated guess. If you're comparing somebody in the same row or the same group, again, anybody further to the right or up will be more electronegative, and usually that will lead to a polar bond if those are the two things involved in the bond. Any questions on any of that there? All right. So as we talked about last time, we have really big differences in electronegativities. Again, if you kind of pull somebody from the left-hand side of the periodic table to the right-hand side of the periodic table, up or right, that's usually going to lead you to an ionic bond. Again, if we're kind of in the same area on the periodic table, which is our non-metal part, we're going to get some type of covalent bond. So again, those are generally our two combinations that lead either to an ionic bond, metal and non-metal, and covalent bond are two non-metals together. Now, when we talk about polar bonds and ionic bonds, as we talked about before, again, that 2 cutoff is not really a sharp for sure cutoff. There are some examples of ionic bonds that are less than 2, but it is sort of a cutoff that we use. Sometimes people will use what is referred to as percent ionic character to describe a bond. And again, it's pretty much what the name implies. If it has 100% ionic character, it is going to be basically an ionic bond. And if it has 0%, it's going to be really a non-polar covalent bond or a pure covalent bond. And somewhere in between will give you a polar type bond. Most people nowadays don't really use the percent ionic characteristic anymore. They usually use polar, non-polar, or ionic, but that's sort of the same idea. All right, so the next thing we're going to talk about, now we understand sort of bonding, how the electrons are shared. We're going to talk about really the steps that you should follow when you want to draw Lewis structures for covalent bonding and molecular compounds, where we do have sharing of electrons basically occurring. Now, I would highly recommend that you do follow these steps because this will lead you to sort of a pretty good picture when it's all said and done. You definitely don't want to do it sort of as piecework with each individual atom and their valence electrons, try to figure out how it comes together. So we don't really want to kind of do it like we do with ionic bonding, where we could kind of figure out these electrons are going to be transferred. So the first thing you want to do is you want to figure out how the molecule or ion is basically put together. There are some sort of rules to follow with that. The major rule is the least electronegative should usually be in the center. And I would say for our purposes here in this particular class, most of the time, everything will be sort of bound to that center atom. It's not always the case. You can have multiple center atoms, but a lot of things that we'll come across in this class will have just one center atom, but it definitely is possible to have more than one. That means that hydrogen and fluorine should never be in the center. Hydrogen, because as we talked about earlier, it should only have 2 electrons, which means if you put hydrogen in the middle, it's definitely going to end up with more than 2 electrons. Fluorine should not be in the center either because it is the most electronegative atom. So obviously the least electronegative should be in there. Probably the most important thing after you sort of figure out the logical arrangement is number 2. And number 2 is the total number of valence electrons that are present in that molecule or that ion that is present. And if you have a neutral molecule, then obviously you don't have to worry about it. You just add up all of the valence electrons Remember that the valence electrons equals the group number on the periodic table. So the group number on the periodic table is where you can figure out the number of valence electrons. Now, if you do have a polyatomic ion, you do need to adjust the electron count if it does have a charge. So if it's an ion, it's going to have a charge. So if you have an anion, which means it has a negative charge, you need to add that negative charge to your total. Otherwise, you're going to be short some electrons. If you have a cation, you need to subtract, and it's actually the positive charge here, positive charge from the total. Again, otherwise you're going to have too many electrons. So if something has a -2 charge, you need to add 2 electrons to your total. If you have like a +1 charge, you need to subtract 1 electron from your total. That number is really important because when you're done with your picture, you have to have exactly that amount of electrons on your picture. Can't have any more, can't have any less. You got to hit that number dead on, that sort of count that you got there. Now, the next thing that you want to do is really sort of important. What we want to think about is these electrons that we just counted up. You really want to think of it as like not necessarily belonging to any particular element in particular. We want to sort of evenly distribute the electrons to everybody within the molecule the best that we can. So what you want to do is basically start with the center atom. And basically what you want to do is make one single bond from the center atom to each of the outside atoms. Again, we're not going to double bond or triple bond out of the box. You're just going to make single bonds. Remember that each of those lines represents 2 electrons, right? So that's equal to 2 electrons. So for example, we would have used 2, 4, and 6 electrons here. Any leftover electrons that you have that you counted up in the previous step will go on the outside atoms first in pairs of electrons. So they should fill up all the outside atoms in pairs of dots until each outside atom has 8 electrons, unless it is hydrogen, which you should never put dots around it because it should only have 2. And what you want to do basically is fill up all the outside atoms first. If at that point you filled up all the outside atoms with electrons and you go to your number that you got previously and you still have electrons that you need to put onto your picture, those then go to the center atom and they also go on as dots. So we're kind of working outside in with those electrons. We're putting them on as dots. At this point, if you find yourself putting some dots on the central atom, you should probably be out of electrons after you do that. So working your way on the outside in. Once you've distributed all the electrons that you counted up in the previous step, the last thing you want to make sure of is that everybody has met the octet rule. And except for obviously hydrogen, that should only have 2 electrons. So if everybody has met the octet rule, then your picture is good. You're done. You can move on, put a box around it, whatever you want to do. If by some chance somebody has not met the octet rule, that is where we want to try a double bond to fix it. So again, we're not going to double bond or triple bond right out of the box. We're going to kind of use double bonds and triple bonds to fix any issues that occur when we do not meet the octet rule. So what you want to do is first try to make a double bond, and if that fixes it, then you're done. If that doesn't fix it, what you want to look at is there any other place I can make a double bond maybe? And if the answer is yes, then you should make another double bond. So you should try to sort of run through all your double bond options. And at some point, if you make a double bond and there's no other options, and everybody is not at 8 electrons, then you want to go off to a triple bond to try to fix it. So again, that's sort of the order. You want to kind of do single bonds first. Everybody's got 8, you're all good. If everybody doesn't have 8, you want to try to fix it with a double bond. If you tried all your double bonds and it still doesn't fix it, then you want to go to your triple bond. So that's the progressive order at which you want to kind of draw these. And if you do that, that will again pretty much give you a pretty good picture when it's all said and done in terms of your Lewis structure. So again, that's what I'm talking about. We want to kind of think about distributing those electrons equally and not necessarily belonging to anybody. So again, not like what we did kind of with like earlier with ionic bonding, where we kind of go, okay, he's got like 5 electrons. This guy's got something, so this electron goes here, this one goes here. We definitely don't want to do that because, again, you're going to end up with probably a picture that doesn't have the right number of electrons, not enough bonds, and stuff like that. So just want to think about distributing those electrons sort of equally to everybody here. All right, so let's do a real one here together and see how that all comes together and works. So if we wanted to draw the Lewis structure for nitrogen trifluoride, first thing we're going to do is basically count up the total number of valence electrons. So 5 for the nitrogen, as that is group 5 on the periodic table. There are 3 fluorines, and each fluorine is group 7 on the periodic table. So that's a grand total of 26 valence electrons for this Lewis structure that I need to draw. Once again, that number is important because we got to hit 26 right on the nose there. Now we want to think about arrangement. And again, I would say just common sense of if you have one element and maybe 3 of the others like we do here, usually the one element's in the center and everybody else is attached to it is usually the way it goes. But we know definitely fluorine cannot be in the middle because it's the most electronegative. So we really do want the least electronegative in the middle. And if we look at the periodic table, that is the run of nitrogen, oxygen, and fluorine. Obviously, fluorine is further to the right in that group and then more electronegative. Now that we have basically our logical arrangement, and to maybe answer a question somebody might have, it does not matter for that third fluorine if you put it on the bottom like I did, or if you want to put it up on top, it's fine too. So if you want to put it up on top, you could do that as well. I'm just going to do, again, one single bond from the center to each of the outside atoms. And again, I'm going to count up how many electrons I've used. Each line represents 2 electrons, so that is 2, 4, and 6 electrons. That means I basically have 20 more electrons that I need to put on my picture. So to put the 20 electrons on my picture, I'm going to work outside in. I'm going to fill up all the outside atoms with electrons, and they're going to be put on as pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. I just put another 18 electrons on there. That means I again still have 2 more electrons to go. All of the outside atoms are filled. So those last 2 electrons will now go to the center atom, also as a pair of electrons are dots. So again, we kind of work outside in to do so. At this point, I now have placed all 26 electrons. Really, the last thing that I want to make sure of is that everybody has met the octet rule. So if we look at each of the fluorines, 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons. And for the nitrogen in the middle, 2, 4, 6, and 8 electrons. So everybody has met the octet rule. We have distributed all 26 of our electrons here. So our picture is good. And this would be the correct Lewis structure here for NF3. Any questions on any of those steps there? Yeah. I subtracted 6, if you're talking about over here. If you're talking about here, that was from my original single bonds that I did. Each of these lines here represents 2 electrons, so that's 2, 4, and 6 by making those first 3 single bonds. Yeah. Other questions? Okay. All right, so why don't you try one here and see what you come up with. Not that one, it's the one we just did. Hopefully we'd come up with the same thing. All right. Why don't you try this one? Why don't you try NO3 minus, a little nitrate. Okay, let's take a look, see how you're doing on this one. Again, we're going to count up the total number of valence electrons here. So we got 5 for our nitrogen, which is group number 5 there on the periodic table. We have, again, 3 oxygens here. Oxygen is group number 6 on the periodic table. But this is nitrate. It does have a -1 charge, and negative charges means that it has gained electrons. So we do need to add that 1 in there for the negative charge, basically. and that's going to be 18, 19, 24 valence electrons in this case. Now, we're going to again kind of put the least electronegative in the center. Also, we do only have 1 nitrogen and 3 oxygens. Once again, oxygen is further to the right there on the periodic table than nitrogen is, and that tells us oxygen is more electronegative, so we wouldn't want to put oxygen in the middle here. So we're just going to arrange it like normal. So we're going to kind of do a nitrogen, just going to put our oxygens around it. And again, it doesn't matter which way you put the oxygen there in the center. You go up or down. We're going to do, again, just a single bond to each of these. So 1, 2, and 3. Again, each of those lines represents 2 electrons. So that's, again, 6 electrons we basically just took off. That leaves us 18 electrons still to go. They're going to go on the outside first in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I've now put on there 18 electrons. I got none left. So really what I want to look at now is I put all 24 electrons on the board there. Is everybody good in terms of 8 electrons? Does all the atoms there have 8 electrons? The answer is no. The nitrogen in the center actually only has 2, 4, and 6 electrons. All the other guys are okay. We got 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. So everybody else has 8 electrons. Nitrogen does not have 8, which means we did not meet the octet rule, which obviously is an important rule for bonding. We always want to make sure we get to the octet rule, as we talked about last time. That's essentially going to get everybody to that noble gas configuration, right, which is that stable configuration. So I need to fix this. Can I fix it by just putting 2 dots there? I cannot do that because now I have a grand total of 26 electrons, right? So too many. So we can't do that. So this is the part where we're going to make a double bond and try to fix it. Now we can make a double bond at any of these oxygens because they're all the same basically. So can I just put a line there? The answer is also no, because I now still have 26 electrons, and the oxygen up on top now has 2, 4, 6, 8, 10 electrons, which is more than 8, which is not good for oxygen. So when we actually do make a double bond, and by the way, when we actually make a triple bond as well, what we have to do is actually bring in a pair of electrons to make that bond. So we're going to take a pair of electrons here from the oxygen up on top, and we're going to basically bring those electrons in to make that bond. And when we do so, that's going to result in a double bond up on top, which have brought those electrons in to make it. Our bonds on the other side are going to remain the same. They're all going to be single bonded. And since this is an ion, we would want to put a little bracket around it and a minus typically. And now what we've done is, if we look at sort of the electrons around everybody, this oxygen has 2, 4, 6, 8 electrons, so it's good. This guy's got 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. And now the nitrogen has 2, 4, 6, 8 electrons. So everybody has 8 electrons around it. And we have still only used 24 total electrons, which again is our goal here, to keep at 24. So when we make the double bond, or even when we make a triple bond, we bring those electrons in to do so. Those electrons are what are referred to as being delocalized, which means they're kind of moving around. And because of that, for example, instead of making my double bond over here, I could have, if I chose to, make the double bond to the right there. And that would give me this picture if I double bonded there to the right. We would end up with the double bond there to the right and not a double bond up on top. There we go. And we have single bond up there. And this would give us a picture. Or we could have actually double bonded there to the left as well, which would have gave us this picture here. and our double bond over here to our left. All three of these pictures are related to each other. These are what are known as resonance structures. And resonance structures basically occur just like we saw here. There was really more than one option where we could have double bonded. And where you have more than one option of where you could have double bonded, you could draw another Lewis structure for that. And that's usually where we see these arrows like that for resonance structures between them. The truth is, as I mentioned before, those double bond electrons in this case are delocalized. And really what that means is at any given point in time, those electrons are kind of moving around, which means they may be up here making a double bond. They may be back over to that side making a double bond. They may be back over to that side making a double bond. So one Lewis structure by itself doesn't really adequately explain sort of the bonding. The true structure is probably between those three. So that's a good question. So you would only need to draw the resonance structures if it asks you to draw all the resonance structures. If it asks you just to draw a Lewis structure for nitrate, any one of those three pictures would be good. Yeah, so you could draw any one of those three. But if it does ask you to draw like all the possible resonance structures or something like that, then technically you would have to draw all three of those there. Other questions? So again, here what we see is a double bond does fix our problem. And again, we don't double bond everything. We just need to kind of start with one at a time and see if it fixes it. And if it didn't, then we would go to two or so forth. Any questions on that one there? All right, let's try a few more here. Maybe let me just write something down. All right, draw the Lewis structure for these things here. Let's go with SO2. Let's go with SH2. Let's go with CH2O. Let's go with NH4 plus. Let's go with N2. And let's have we'll do HNO3, which is nitric acid. Forget it. And just to let you know, nitric acid, one of the hydrogens is attached to an oxygen. All right, so give it a try, see what you come up with. Take some time here, draw some Lewis structures. One more, we're gonna do CO2 as well. Okay, let's take a look, see how you're doing through this list here. We'll start with the first one. So go SO2. So again, we really want to count up our valence electrons here. So sulfur is group 6, so it should be 6. We have 2 oxygens, which are also group 6, and that's going to give us 18 valence electrons in this case. When we look at sulfur and oxygen on the periodic table, it looks like this. Oxygen is further up on the periodic table, which means it's more electronegative in that group, and that means sulfur actually should be in the center. We are going to just put our oxygens to the side, is probably the best move. Again, following our same sort of rule here, we're just going to do a single bond to each of them. That is 4 electrons, which means we have 14 more to go. That's going to go on the outside first. So 2, 4, 6, 8, 10, 12. At this point, I have now put on a grand total of 16 electrons. I actually still have 2 electrons to go. That then goes to the center also as a pair of electrons. So we should have a pair of electrons right there. And that would get us to, obviously to our 0 in terms of electrons. Yeah. The middle one does need 8, and that's what we should look at this point once we've distributed all 18 of our electrons. And what we want to look at is make sure everybody has the octet rule. So if we look at the oxygens here on both sides, since they're basically the same, it does have 8 electrons around it, 2, 4, 6, and 8. But you are correct here. If we look at the sulfur in the middle, it has only 2, 4, and 6 electrons. So this is not a good situation, obviously, for our sulfur. So we do need to fix it. Again, we're going to first try to fix it by making a double bond. And in this case, each of the oxygens are the same. So you can double bond on either side. Remember, as we talked about before, we're going to take a pair of electrons and basically move them in to do so. And if I do that, that will get me a double bond here on my right and a single bond on my left. We could have as well double bonded on the left and give us a resonance structure that would look like this. And again, either one of those would have been perfectly fine to do. We now have, in terms of our center sulfur, we do have 8. So 2, 4, 6, 8. Oxygen here, 2, 4, 6, 8. Oxygen here, 2, 4, 6, and 8. So again, at this point, everybody will have 8 valence electrons around it. We still have only 18 electrons, and we're good. And by the way, following our steps, that is how we get those dots on the central atom. It should have dots. It should not have 2 double bonds on each side, which is like what people like to always draw with this one. Any questions on that there? All right, so taking a look at the next one here, we'll just kind of put a box that way. SH2, so again, sulfur is 6. There are 2 hydrogens each out. 1 is 8 valence electrons here. Obviously, in this case, sulfur has to go in the middle because we should never put hydrogen in the middle. So just going to arrange it just like we did previously. Once again, we're just going to do a single bond to each of the outside. At this point, that's going to be 4 electrons that I've used. I got 4 more to go. Can I put dots on hydrogen? I cannot because hydrogen is full. So hydrogen should only look like that, basically, a line to it and nothing else. So because hydrogen is full on both of those, the next place we have to go is now to the center. And just like normal, we're going to put them on as pairs of electrons. So we're going to put them on like so. And that will give us all 8 of our electrons put up there. And now everybody is good. Remember, again, hydrogen only needs 2. So it's got 2 on each side. Sulfur's got 2, 4, 6, and 8. So it is good as well. Any questions on that one there? Next up is CH2O. So again, figuring out our valence electrons here. We got 4 for the carbon, 2 times 1 for the hydrogen, and our oxygen there is 6. So that is 12 electrons here. In this case, once again, hydrogen should not be in the center. And if we look at the periodic table, we got carbon, nitrogen, oxygen, fluorine in that row. And again, oxygen is further to the right, which means it's more electronegative. So the least electronegative is carbon in this case. And carbon should go in the middle with our hydrogens around and an oxygen obviously on the outside as well. So again, we do want to put the least electronegative atom in the center in most cases. All right, so still going to do the same thing. We're just going to do a single bond from the center to the outside. That again is going to give us 2 per line, so that's 6 electrons. We have 6 more to go. At this point, we cannot again put any dots on the hydrogen because it is filled, but the outside oxygen is good. We have places to do that there, so we could go 2, 4, and 6. At this point, we have now put on all 12 of our electrons. So once we do that, we then want to make sure everybody has 8. And hopefully you can see that it is the carbon here that is a little short. It has only 6 electrons around it. It has basically 2, 4, and 6. Each of the hydrogens are good because they have 2. And the oxygen on top is good because it has 8. So again here, double bond we want to try to do to fix it. We are going to take that pair of electrons in to make that double bond. And when we do so, we will end up with something that looks like this with a double bond there. And now at this point, we should be in business. We got 2, 4, 6, 8 electrons there, 2 there, 2 there. And for our carbon, 2, 4, 6, 8 electrons. So again, everybody has 8 except for hydrogen that has 2. Still only have 12 total valence electrons in this case. And that would be our correct structure without all the highlighting, probably. See if I could do that without killing the structure here. Close enough. Any questions on that particular one there? All right, NH4, I'm going to flip the page here. NH4 plus N2. Well, nitric acid, and I did CO2 there. All right, so let's take a look at these here. Again, following our same sort of steps, we'll do NH4 plus first. So NH4 plus, again, 5 for the nitrogen. Each hydrogen is 1. In this case, though, we do have a plus sign, and remember, plus means that it has lost electrons. So we do need to subtract 1 from that. That's going to give me 9 minus 1, which is 8 valence electrons. Clearly, as we've been talking about, hydrogen cannot go in the center, so that leaves you just one option, which is nitrogen in the center, hydrogen around. Once again, just going to do a single bond to each. That is 2, 4, 6, 8 electrons. That is the picture right there. We put a little bracket and a positive sign around it. Each hydrogen has 2 in this case, so 2, 2, 2, and 2. And nitrogen has 2, 4, 6, and 8, so it is good all the way around there. Any questions on that one there? All right, so next one is nitrogen, a little N2 action here. So that is 2 times 5, which is 10 valence electrons. There really is no center atom in this case, so you just kind of put them side by side, will work. And you could still just follow the same sort of rule that we've been doing, which is I'm just going to first connect them with a single line. So we're just going to do a single line there. That obviously is 2 electrons. We got 8 to go. You're going to put them on the outside. It doesn't really matter which nitrogen you choose. So we'll go 2, 4, 6, and 8. In this particular case, our nitrogen on the right there is good. The nitrogen on the left is quite short. It has only 4 electrons. It's got 2 here and 2 here, which is 4, which gives it not enough. So again, in this case, we're going to try to fix it by making a double bond. So we'll take a pair of electrons from our nitrogen on the right in this example and bring them in to do so. That is going to give us a double bonded nitrogen. Did that fix the problem here? It did not. It got better, and our nitrogen on the left now has 6, but it still doesn't have 8. The one on the right here still has 8. So now we have no other place to make a double bond. So now we want to move to a triple bond. And the triple bond again works the same way. We're going to take another pair of electrons and basically bring them in to make that triple bond. And now we will end up with a triple bonded nitrogen. And each of them also has a pair of non-bonding electron pairs, and that is going to give us 8 electrons for each of them. A grand total of still 10 electrons on the picture, and everybody should be good at this case and how nitrogen gets to a triple bond in that case. Any questions on that one there? All right. The next one we're going to look at is nitric acid, and as I mentioned before, in the description, the hydrogen is attached in this case to an oxygen. And again, if it is something that maybe you're not familiar with or can't really figure out, I probably will tell you kind of like this sort of connectivity. We're going to do the same thing here. We're going to take hydrogen, which is 1, nitrogen, which is 5, and 3 oxygens, which is 3 times 6. That's 18, 19, 24 valence electrons in this case. Now, in this case, nitrogen is going to be in the center. Again, looking at the periodic table, NOF. So nitrogen is least electronegative. I'm going to put the oxygens around. And as it says here, the hydrogen is not attached to the nitrogen, but it's actually attached to a oxygen. So I'm going to put the hydrogen over there. It doesn't really matter which oxygen you chose there. You can put the hydrogen on any of the oxygens, and it's all good. But I'm just going to put mine to the right here. So in this case, we actually have more than one central atom. We have a nitrogen that's like a central atom, and we also have one of the oxygens next to the hydrogen there. That's also considered a central atom. So although probably not too often in this class, you'll have something that has multiple central atoms, it definitely is obviously possible to have something like that. We still work it the same way, which means we're just going to connect everybody here with a single bond. So we're just going to single bond it up here all the way across. And again, in this case, we did 4 single bonds. Each counts as 2 electrons, so that's 8 electrons in this case. And that's going to give us 16 more to go. We're still going to work outside in. So obviously here, we're not going to do anything to the hydrogen because it's good. So we'll put some electrons on the outside, oxygen. So 2, 4, 6, 8, 10, 12. At this point, I have now put on my picture 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons total. That means I still have 4 more to go. And the next sort of outside atom, in this case, kind of working outside in, is actually the oxygen. So we would put a couple pairs of electrons on our oxygen, and that's going to take up our 4, and now we're at 0. So we now have on our picture all 24 electrons, again, working outside in. We want to check to make sure everybody's good in terms of 8 electrons. And hopefully you can see right here, our nitrogen is a little short. It has 6 electrons. Everybody else is good. All the other oxygens have 8, and the hydrogen has 2. So in this case, we're going to fix it by making a double bond. And in this case, we really have 3 options to make the double bond, but most cases, you would probably either choose this one or this one. The reason for that is kind of, that's what makes it an acid, actually, that one right there. So you probably don't want to play too much with that. That's the hydrogen that actually pops off to make it an acid. So we're going to do the same thing. We're going to take a pair of electrons and move them in to do so. And if I do that there, we'll end up with a double bond up on top. We'll still have our single bonded there, and we'll still have our single bonded there. This also could be a resonance structure because we could have also double bonded here instead on the bottom left there. And if we drew that, we would end up with a picture that looks like this with our double bonded oxygen over here to the left. So we could also draw a couple of resonance structures for this as well. Any questions on that one? Yeah.
So double bond with the oxygen.
It would not. There's some things that we're probably not going to talk about in this class. Reasons why you probably maybe wouldn't do that. And some things are known as formal charge, which has a lot to do with. There are, for example, multiple ways you can kind of connect things sometimes, and some ways are better than the other based on what's known as formal charge. And so to answer your question, technically it wouldn't be wrong. Technically, it is possible that that could happen. It would not be like a good structure per se versus maybe the other 2 that we have here. So you can sometimes use, and you'll do this probably in 1A more than we would probably do it here. But in 1A, when you calculate formal charge, you could pick a Lewis structure that's like a kind of best, better, good, not so good, based on sort of formal charge and where those charges end up and stuff like that. Because by kind of double bonding into here, that's going to create a charge on the oxygen that may not be great in that situation because oxygen is more electronegative. Other questions on that? So what will happen, for example, if he did this? And he double bonded here, like so. And you got that. So in this particular case, what will happen to the oxygen is it actually has a +1 sort of charge in this situation. And that's not really good. You technically don't really want like a positive sort of formal charge on like a more electronegative atom and stuff like that. So that's why that one necessarily would not be the best structure. Other questions? All right. Last one here is CO2. And in this particular case, 4 plus 2 times 6, which is 12, and 4 is 16. In this case, once again, just looking at the electronegativity and everybody's in the same row, carbon obviously is less electronegative than oxygen. And like I said before, typically if you got like one element and a bunch of others, usually the one element's kind of in the middle and everybody else is attached to it. So we're going to do a carbon, oxygen, again, a single bond to each. That's going to give us 4 electrons. We got 12 more to go. We're going to go on the outside first here. So that's going to go 2, 4, 6, 8, 10, and 12. So obviously at this point, I have put in all of my electrons. And you probably can just visually see that carbon is well short there. It's got 4 electrons basically around it. So here we're going to double bond to try to fix it. So just like we've done previously, we're going to take a pair of electrons in to do so. That's going to double bond me up here like so. And at this point, what that does to our carbon in the center is it makes it a little bit better. It's now got 6, but still short of 8. At this point, we actually do have an option to double bond the oxygen on the left. And that is actually what we want to do. So again, typically speaking, you kind of want to exhaust all your double bond options if there's more than one and it doesn't fix it. So that is typically what we would want to do, which is bring those electrons in on this side. And that's going to give us now a double bond on the other side. And you will end up with a picture like this, which is what CO2 looks like. To sort of tie into the question that was asked a second ago, if you decided, hey, why can't I just like triple bond that thing instead of like double bonding, right? So if we were to, for example, instead of doing what we did here and just triple bond and brought something in, we would end up with a triple bonded over here, and we would still have our single bonded over here. And technically speaking, everybody's good, right? Everybody's got 8 electrons and all that good stuff. And it does come down to what I was talking about before, which is formal charge. For example, if we were to calculate the formal charge, which is essentially the charge on each of these atoms, how they're bonded together, to calculate what's known as formal charge, you take the number of valence electrons in the atom, you minus the number of non-bonding electrons, which are the dots basically, right? And you minus the number of bonds. So for example, if we did it for this oxygen here, the formal charge on that oxygen would be 6 minus 2, 4, 6 non-bonding electrons minus 1 bond, which gives us a -1 sort of charge on that guy. So in this arrangement, that oxygen is kind of carrying like a -1 charge. If we do it for the carbon here, we basically have for our carbon 4, which is the valence electrons of carbon, minus 0 as there's no non-bonding electrons present, no dots on that carbon, and minus 4 bonds, which is 0. So we have 0 there. Now if we go to this triple bonded oxygen here, so this is our single oxygen, this is our carbon, and now if we do our triple bonded oxygen, it would be for the formal charge 6 for the electrons in oxygen, minus 2 for the 2 dots, minus 3, which is +1. So we'll end up with a +1. Now overall, it does equal 0, the charges, right? +1, 0, and -1 equals 0. And those would be sort of the formal charges that we would have on this. Now if we did the same thing for this guy, and we did our double bonded oxygen, the formal charge here would be 6 minus 4 for the 4 dots, minus 2 for the 2 lines, is 0. If we do it for the oxygen on this side, it will also be 0 because it's going to come out the exact same calculation. If we do it for our carbon in the middle, it would be 4 for carbon, minus 0 because there's no dots, minus 4 lines, which is 0. What the one that has the double bonds has in favor of itself is when you look at like Lewis structures for formal charges, the best situation you could have is if everybody hits zeros. Yeah. So when we look at the one that's double bonded, the formal charge for all those atoms are zeros, which is like the best situation you could have. This has small formal charges, but what we also have here is a positive formal charge on a more electronegative atom than, say, carbon, and that's not a good situation. So for those reasons, which again, we're not going to go too deep into, there are reasons why, and we want to kind of follow those rules because usually it'll give you a fairly good structure based even on formal charge in most cases. You'll kind of end up with the right structure. So again, if you just follow those rules like single, exhaust all your doubles, and then triple for your last resort, you usually will end up with a much better picture than double bonding or triple bonding out of the box. Any questions on that there? Now, to be truthfully honest with you, that's not always the case that you'll end up with the best picture based on formal charge. But for our class, that's really what you should follow. And like I said, when you get into 1A, you'll kind of use formal charge to help you decide, which one's a better picture. So if you decide to do that, you would definitely want to choose this one based on formal charge for sure. It zeroes out all the atoms to a much better sharing of electrons. Basically, what those zeros mean is those electrons are kind of being shared nice and equally around everybody, rather than here, we got a lot more electron density on this guy than we do here. And, since they're both oxygens, that shouldn't really happen in that case. Yeah. Other questions on how to draw Lewis structures? All right. So clearly you need to draw Lewis structures and know how to draw them. So here's CO2. We'll just go through this guy here. And all right, so let's talk a little bit more about resonance. But before we do, let's talk a little bit about bond length. And bond length is the distance between the two atoms within a bond. And you don't have to obviously memorize any of these numbers on this page, but we can use it to help us look at what's happening in terms of the distance between the atoms and as we make bonds. So for example, the carbon-carbon single bond's 154 picometers, the double bond's 133, and the triple bond's 120. When we look at a carbon-nitrogen bond, single 143, 138, and 116 for double and triple bond. What we actually see here is as you put on more bonds, the distance between the two atoms gets smaller. So a single bond is longer than a double bond, and it's longer than a triple bond. And what happens if you think about it, remember that there is like a positive charge for the nucleuses right on each of those guys and those atoms, and we bring the electrons in, right, as we just saw in our Lewis structure, to make that double bond. So you bring a lot more negative between those two, and that's just going to bring everybody closer together. When you make a triple bond, you bring those electrons in, more electrons to the center, going to kind of pull everybody tighter and closer together. So every time you put on a bond, the distance between the atoms gets smaller and smaller because it's just bringing everybody closer together, because there's a bigger negative charge between the two atoms that's going to draw everybody in. And that does have a big effect on bond strength. So when we talk about bond strength, a triple bond is typically stronger than a double bond, and a double bond is typically stronger than a single bond. By the way, both of these sort of trends, if you will, are not like perfect. So what I mean by that is like a single bond is not like our double bond is not twice as small as a single bond. A triple bond is not 3 times as strong as a single bond or anything like that, but that's just the general trend. I think of it like a pencil. If you have like a brand new pencil right out of the box, you could take that thing and you could snap it pretty easily, right? It's going to crack in half, no problem. If you take like a chemistry test and you got like just a little bit of a pencil left and an eraser and it's like this big, you're going to have a very hard time if you want to try to break that pencil in half, right? Because it's just like everything's way too close together, and it's going to take a lot of strength to try to break it in half, right? Rather than when it's spread out apart in big brand new pencil, you could break it pretty easily. And that also is what's happening here again as we bring all that electron density towards the center. It's just a lot of strength and things held really, really tightly. So it's going to take a lot more energy to kind of break that. Now, resonance structure, as we talked about, typically does occur again when we have more than one option, for example, of putting our double bond. Again, we typically draw those arrows between them to indicate there's more than one structure. And it's really because those double bond electrons and really the triple bond electrons are delocalized. Again, they're moving around. They're not necessarily just like attached to one atom. That's what's known as localized electrons. They're basically stuck on that atom. They're not going to move anywhere. But these delocalized electrons can move around, And again, that's why we have the option of we could double bond over here to this oxygen, or we could have done it to the top oxygen, or the one to the right. And a couple of examples, for example, this is ozone. If you draw ozone, those are just the formal charges on ozone, but so you don't have to worry about it. But it looks something like this. And again, you could have double bonded like you see down there to our right-hand side here. And again, those electrons are basically being moved around. Another example is carbonate. And again, carbonate looks just like nitrate. And again, it has one double bond, but you can double bond into either of those three oxygens. Again, the true structure is probably somewhere between all three of those, as those double bond electrons, again, are kind of moving around from one oxygen to the next at any given point in time. A benzene ring is something that you might see if you take organic. Looks something like this. Yeah, it's not half bad. There we go. And this is line structure, and line structure in organic chemistry basically means each of these things are carbons. These are all carbons. And each of these actually has a hydrogen as well attached to it, although you typically don't draw it when you're doing this. And it has three double bonds, basically. So you can draw benzene like so. It could also make a resin structure where those basically double bonds move around to the opposite side. And that's why you may even see benzene sometimes drawn, which is like a circle in the middle. And that circle indicates that it has those three double bonds, and those electrons are basically moving around the ring and can kind of shift back and forth between them. Again, if you take organic, you'll draw that picture nonstop a lot. All right. So resin structures, again, as we talked about earlier, you don't necessarily have to draw all the resin structures unless obviously the instructions ask you to do so. If again you're asked to draw a Lewis structure, you could draw any one of the resin structures, and it's all good. So here's just another example. Obviously, you got 4 different resin structures for this particular one. And again, each of those pluses and minuses are actually the formal charges on each of those atoms, but you don't have to worry about that. So let's talk a little bit about the octet rule. And obviously in this class, for sure, pretty much everything is going to obey the octet rule. But there are some exceptions to the octet rule. And let's talk about the exceptions. The first exception is an incomplete octet. And there are certain elements that is perfectly fine with less than 8 electrons around it. And that is the big 3 here of typically beryllium, boron, and aluminum. And I would say out of those 3, probably boron is the one that you will see the most in terms of less than 8 electrons. Boron and aluminum typically will go 6. Beryllium will typically go 4. But boron is very, very common in terms of an incomplete octet. So here we have beryllium with 2 hydrogens, and again, it is technically fine with 4 electrons. And again, boron here is actually pretty much good with 6 electrons. These things are also sometimes referred to as being electron deficient. And in 1B, you'll learn about boron trifluoride. And basically, this is what makes it a Lewis acid. So it actually can act as an acid because it's actually missing electrons. So when something like that's electron deficient, it can actually act as an acid in certain situations. And it's known as a Lewis acid in that particular case. So one exception to the octet rule is less than 8, which is known as an incomplete octet. The next sort of exceptions to the octet rule is an odd electron molecule. So when you add up your electrons, you end up with an odd number. And what that means is you will end up with 1 unpaired electron, basically. And that is what is sometimes referred to as a free radical because it has 1 unpaired electron. that also makes it quite reactive because it kind of wants to fix that situation. Free radicals a lot of times happen in atmospheric chemistry, like with chlorine happens a lot with it. You get this unpaired electron, makes it very, very reactive. And again, trying to fix that situation. The last exception to the octet rule, which as you continue on with your chemistry career in 1A, that you will see probably the most out of all three of these, is the expanded octet. And the expanded octet is one that you'll see the most definitely in the next class that you take. And there are certain elements that could actually go more than 8. And that's why it's known as an expanded octet. And that typically is on the periodic table right there at sulfur. We go left, you go right, and go down in the non-metal region. That is the elements that typically can go over 8. Now, why could they go over 8? Because if you look where sulfur is on the periodic table, that's in period number 3 on the periodic table. And if you remember from electron configuration, period number 3 is the third energy level, the n equals 3 energy level. And if you remember, what orbitals begin on the third energy level? We have s's, we have p's, and this is the first energy level where d orbitals begin. And because they have the d orbitals available to them, they're able to have a place to stash all those electrons. So even though they may not be using them, they have those orbitals available to them to put the extra electrons, which allows them to go over 8 electrons and make this expanded octet. That also means, by the way, if you go one period above them, nitrogen, carbon, nitrogen, oxygen, fluorine, that is the second energy level. And on the second energy level, they only have s's and p orbitals. They actually do not have d orbitals. So anybody in this period on the periodic table can never go over 8 because they don't have those d orbitals available to them. So they should never ever go over 8, those guys. But the ones below can definitely go over 8. So for example, SF6, I won't draw all the dots, but I'll just draw the connections. We basically have 6 fluorines around it. And if we count up around the sulfur, 2, 4, 6, 8, 10, and 12 valence electrons, and it's perfectly fine with that. So these guys that can do the expanded octet can go 10 or 12. But in here in our class, we typically will not draw things that go into the expanded octet. So we will obey the octet rule. But just to tie it together with something we were just talking about, if you went through and drew the Lewis structure for SO42- with our steps, you would end up with a Lewis structure that looks like this. And this would be good. Everybody has met the octet rule and everything like that. Now, if you Google the picture, whatever it may be, or ask somebody to draw you might see online something that looks like this, which also has the correct number of electrons for sulfate. But when we look at the sulfur here, it has 2, 4, 6, 8, 10, and 12. It actually is an expanded octet. And the reason you see this online is for what we were talking about before. In this particular case, based on formal charge, this is actually the better structure based on formal charge, as opposed to this guy where each of these are like -1, -1, -1, -1. And then the sulfur here in the middle is basically +2. Over here, this is -1, -1, 0, 0, and 0 in terms of formal charge. So actually in this particular example, by going into the expanded octet, it's actually a much better Lewis structure than the one we would get for our rules. But in this class, you should end up at this one because we're not drawing this one. Yeah.